Welcome to our video tutorial here involving graphing rational functions by hand. Specifically rational functions that are going to end up having a slant asymptote. So we see the rational function written on the screen, and to get things started here, let's go ahead and factor the function r of x, both in its numerator and denominator, though the denominator is already good to go at just x plus 1. Up in the numerator, it'll factor into x plus 4 times x minus 1. Now we're going to use both of those forms, the original function form and this factored form, in an analysis of the problem. Let's start off with our x-intercepts. X-intercepts are going to be at negative 4 comma 0, because when we plug in negative 4, the numerator is 0 and the denominator is non-zero. And at 1 comma 0, because again, plugging in x equals 1 makes the numerator 0 and the denominator non-zero. The y-intercept is where we plug in x equals 0. I like to go back to the original form, because if x is 0, the x's are gone, we get negative 4 over 1, which will just be a negative 4. The domain in this problem is just going to be the fact that x is not equal to a negative 1. What's happening at negative 1? Well, that's a vertical asymptote. So then we have to do our vertical asymptote behavior to figure out what's happening on each side of x equals negative 1. So we're going to look at negative 1 from the left, and we're going to look at what's happening at negative 1 from the right of our function r of x. From the left-hand side, when we plug into the numerator a value like negative 1, we get a positive and a negative, and then in the denominator we get 0. But if we're plugging in a number slightly less than negative 1, like negative 1.1, the denominator is going to be negative. And over here, if we're plugging in a number slightly greater than negative 1, say negative 0.9, this is going to be close to 0, but it's going to be a little bit larger than 0. Notice the numerator should not change signs on different sides here. If we plug in negative 1, we're still getting a positive and a negative up front. So 2 negatives and a positive will be a positive infinity. 1 negative will be a negative infinity. There is our vertical asymptote behavior. Now the other thing in this problem that we have to be mindful of is what's happening as the end behavior. If we look at the end behavior, r of x, the largest power in the numerator is x squared, the largest power in the denominator is x, but we can't really specify, because that's just going to turn out to be an infinity. The way we specify what happens when x gets really large is to do the division. So we're going to go ahead here and do a synthetic division because we're able to do so. 1, 3, negative 4. Slide the 1 down, multiply here. And what we end up with is the following, that the numerator, x squared plus 3x minus 4, is equal to the divisor, x plus 1, times our quotient. In this case, the quotient was x plus 2, and then plus the remainder of a negative 6. But here comes the key to the problem. When we divide through by x plus 1, divide through by x plus 1, divide through by x plus 1, we achieve the following, that this r of x, that was our original function, r of x is equal to x plus 2 minus 6 over x plus 1. This x plus 2, when x gets really large, really large, like positive infinity, this goes away, because 6 divided by a large number becomes like 0. This x plus 2 turns into the slant asymptote, or what we might call the end behavior asymptote. Either way, it's going to be y is equal to x plus 2. The other question that we have to ask is, does this function cross its slant asymptote? So to determine that, one way we could do it is take the asymptote, x plus 2, and set it equal to our function. Go back to the original form as desirable here. X squared plus 3x minus 4 all over x plus 1. Now if we're solving that equation, we can multiply both sides by x plus 1. So x plus 2 times x plus 1 equals x squared plus 3x minus 4. Foil out our left-hand side. And look what happens. x squareds cancel, and the 3x's cancel, leaving us with 2 is equal to -4. No, that never happens, and there will not be a cross to our to our slant asymptote. The other place that you could look is up here at the remainder. Is the remainder ever going to equal 0? No. This term right here that I'm going to circle in red, this term would have to be equal to 0 if the function was equal to its slant asymptote and they crossed. It isn't. It can't be equal to 0. 6 cannot be equal to 0. Hence, again, there's no cross to the slant asymptote. With all of this being said, we can now go ahead and sketch the graph of this function. So we get our axes on the screen. We'll label them as x and y. And now let's label the key components of this function. So up here we had x-intercepts at -4 and +1. Over here we'll put an x-intercept at -4. Please label it. And +1. Our y-intercept was down at 0, -4. And again, you don't have to worry about drawing things perfectly to scale. We had our vertical asymptote at x equals -1. Make sure that we label our vertical asymptote as x equals -1. Our slant asymptote was y equals x plus 2. And again, things do not have to be drawn perfectly to scale. But that said, they still have to fit into where they belong. So y equals x plus 2 is going to look like this. Make sure you graph it carefully. Y equals x plus 2 is going to go through the point 0, 2, that's its y-intercept, and it's going to go through the point -2, 0. So make sure you've got things in the right location. It doesn't ever cross its slant asymptote, and it doesn't ever cross its vertical asymptote. So now it's just a matter of drawing this function once we put the vertical asymptote behavior on our graph. -1 from the left goes to +infinity, and -1 from the right goes to -infinity. And now we just connect the dots. It's going to come down through here. It's got to go through this point, and it's got to get close to this asymptote, something like that. I know that's not the best drawn graph. Maybe you would say, well, let me try to draw it a little bit better here, a little bit more smooth on how it's drawn. That's fine. Make sure it gets close to your asymptote but doesn't cross. And over here it's got to come up, go through this point, and get closer and closer and closer to our asymptote. I didn't draw that particularly well. And sometimes with the screen technology it can be a little difficult. But make sure it looks like you're getting close to your asymptote. And the better that you can draw this, the more coherent you can draw it, the better. But these are the key features that I need to see. Labeling of the x-intercepts, labeling of the slant asymptote with its key intersection points, labeling of our vertical asymptote, and then the graph the rest of the way. So again, keep track of things as you go. If you have a situation where the degree of the numerator is greater than the degree of the denominator, that's when you get the slant asymptote, and that's when you have to go through and do this particular analysis.